In this video, I'd like to introduce a method of factoring quartic polynomial. It means polynomials of degree 4. Let me erase that. Alright, I think I fixed it. Here's a polynomial, a typical polynomial of degree 4. And here, the coefficient we're considering are all integers. And factoring means we are factoring this polynomial over integer coefficients. So actually, our goal here is rewriting this polynomial, we have it here, into a product of two polynomials like this, where they have coefficients, all integers. Like this, they have integer coefficients, and each of the degree of each polynomial here is of course more than or equal to 1. Like this. So that's our goal. And there is a well-known theorem to do this type of factoring of higher degree polynomial, something called rational zero theorem. So here it's written, it's called rational zero theorem, and this method actually completes. So this method really completes the case of degree 3, a polynomial of degree 3. If degree 3 polynomial is factored, if you think about it in terms of degree, it's a polynomial degree, it adds up. So if you factor into two things, it's either degree 1 or degree 2, or degree 1, and degree 1. If you think about it, these two are the only cases that factors. But there are polynomials, it does not factor over these integer coefficients. And by doing this rational zero theorem, relatively quickly, you can decide whether it's going to factor into these degree of polynomials, or it doesn't factor at all. So using just this rational zero theorem, the theory is complete. But if you enter degree 4 case, this is still very useful, but there is this one other cases we have to take care of, and that is the main discussion of this video. This method can be extended to a higher and higher degree, but the method of searching, it gets more complicated and extensive, so it is not very effective. But while the search we're about to go through is fairly effective for the degree 4 case, so we're discussing here. So here's the polynomial, and I wrote this rational zero theorem again. So again, let's think about in terms of degree and how this can factor. Of course, the first case we can think about it when it factors completely then and over the integers, not using complex numbers or complicated real number, just over these whole number integers. Let's think about the case where there is a degree 1. So that means 4 is factored into there is a degree 1 and rest of the pot is degree 3. So how further it factors, maybe this 3 factors into two different cases, maybe it factors like this, or it doesn't factor at all, or it factors completely like this. Sorry about this, it should be 2. Should be 2 over here. Or it completely factors. If you think about it, I think this is it. It doesn't factor and factor into two parts, or factor into 3 parts. All of these cases has this degree 1 factor, and whenever it has degree 1 factor with a rational coefficient, the rational zero theorem will catch it. So let me remind you of the rational zero theorem. So if I write it RZT, the rational zero theorem says we should try x equals all sorts of number that looks like this p divided by q, where q is an integer factor of e and p is an integer factor of a, including all the sign possibilities. So I wrote it here. Q came from some factors of e, p came from some factors of a, and here we noted that p and q may be negative, right? So those are the possibilities. So there's this rational zero case will always find this factor, and once you find that factor here, rest of the pot is degree 3. So you can check again using the rational zero theorem whether it's going to factor or not. Like I claimed it before, this rational zero theorem completes the case of degree 3 case here. So the case there is linear factor, if it is degree 4 case, and the rational zero theorem will take care of it. So I will say it's done here.